The story of NASA's Langley Research Center is the story of taking what seems impossible and making it reality. It began just 14 years after the Wright brothers achieved the elusive, some said preposterous, goal of powered flight, a goal chased by humankind for millennia. Their 120-foot journey at Kitty Hawk, North Carolina in 1903 broke the impossibility barrier, setting the course for the next century and beyond. The United States invented the first successful airplane, but European countries brought aviation to new heights. From the start, a number of European governments funded aeronautics research, which paid off when World War I broke out in 1914. Even before the war, aviation leaders realized the U.S. was falling behind and pressed Washington to do something about it. So in 1915, Congress authorized $5,000 to create the National Advisory Committee for Aeronautics, the NACA. This little seed, planted in the fertile farmland of Hampton, Virginia in 1917, grew to become NASA Langley, America's first civilian aeronautics research lab and NASA's first center. And it's been reaching for the impossible ever since.
To go to the moon in this decade, not because they are easy, but because they are hard.
The National Advisory Committee for Aeronautics facility began as administrative offices and a wind tunnel building on rural land that the U.S. Air Service wasn't using. The NACA broke ground for the Langley Memorial Aeronautical Laboratory on July 17, 1917. Topographically, it was a swamp, but geographically, it was ideal.
Hampton was really the perfect area for a facility like Langley. The U.S. Army Air Service was already there, so there was already flying going on. And what the engineers liked was the fact that it was a pretty good distance from Washington. So the suits were up there and the engineers had Langley to themselves.
World War I had shown aircraft's need for more speed, power, and agility. Not just in wartime, but for untapped commercial possibilities. It was for that reason Langley was conceived as a truly national laboratory, to benefit aeronautical exploration. From the start, Langley dedicated itself to building the tools, setting the rules, and solving the problems that kept flight from reaching its potential.
At the time Langley was established, the potential for aeronautics was as big as the sky. There was no place to go literally but up. The United States was really far behind Europe in terms of aeronautical research and progress. The Europeans, after all, had been driven by the fear of war and then an actual war, lots of money going into the technology. In this country, not so much. And the founders of the NACA recognized just how important those European labs had been in pushing European aeronautics.
Langley came online as America's first civilian aeronautical research lab in 1920. The NACA's first atmospheric wind tunnel was already at work testing aerodynamic forces that affect aircraft. It was a good beginning, but by no means state of the art. The aerodynamicists knew they needed to do better, a lot better. And they did. 2 years later, in 1922, they powered up a new device no one had ever seen before. The world's first pressurized wind tunnel, the Variable Density Tunnel.
One of the things they did with it early on was to run a whole string of airfoil tests, just all kinds of airfoil shapes. And they published the data in kind of a catalog that was really of revolutionary importance for airplane designers. You could go to the NACA catalog, you could pick out an airfoil that had the characteristics you wanted, and there you go.
These reports, still used by aircraft designers today, kicked off Langley's reputation as a preeminent research facility. The value of Langley's wind tunnels came early. In 1928, Langley engineer Fred Weick used the propeller research tunnel to design a cowling or cover for propeller engines that reduced drag, cooled the engine, and increased an aircraft's flight speed.
And it was those sorts of improvements coming out of the NACA that really laid the foundation for the advance of both military and commercial aviation in this country.
Success followed success. Encouraged by the propeller research tunnel, which was big enough for a full-size aircraft minus the wings, Langley built a tunnel to test entire planes, wings and all. In 1931, Langley opened the full-scale tunnel, which could test at speeds up to 118 miles per hour.
You really can't talk about the history of aeronautical research at Langley without talking about those wind tunnels. As you get into the mid and late 1930s, Langley, on the basis of the airfoil research, the cowling, and all of the other work they were doing, had established itself, the engineers had established themselves as a match for anybody else in the world. The Germans, the English, Langley was right there contributing to the body of knowledge.
And when the winds of war began to blow, Langley's tunnels were ready to serve. Many believed we would never beat Germany's superior air power. And based on how things looked at the end of World War I, that would be a reasonable assumption. But a lot had changed in one generation.
During the war, I think the lights never went out at Langley Research Center. The full-scale tunnel, I mean, you could put a full-scale fighter with a 40-foot wingspan in that tunnel and do really important tests with it.
Those tests were possible in part because of women who filled critically important jobs in machine shops, laboratories, and offices, while men were at war.
The Langley Research Center just played an incredibly important role during World War II, as it had in the years leading up to the war.
After the war, the innovations kept coming to increase structural integrity, safety, and speed. But how fast could we go?
Speed was, at that time, one of the things that aeronautics was all about, after all. And Langley, from the days of the NAC cowling and the other advancements, had certainly done its part to build speed. By the late 1930s and during the war, it became clear to engineers, though, that there was a real problem on the horizon.
That problem was the sound barrier. During World War II, pilots noted that in steep dives, as aircraft approached the speed of sound, Mach 1, they would behave differently than at slower speeds. Langley's tunnels would again be needed to solve that problem, but first the tunnels themselves had to change.
The 8-foot high-speed wind tunnel could handle speeds of up to 500 miles an hour. When you get air much faster than that flowing through a normal tunnel, it began to create all sorts of problems with the reaction of the air to the wall of the tunnel, and you weren't getting good data anymore.
In the late 1940s, Langley's Ray Wright, with the support of Division Chief John Stack, experimented with ways to relieve these effects so that testing at transonic speeds could be done. They developed what they called the slotted throat wind tunnel.
You'd always been able to test at supersonic speeds and, of course, at subsonic speeds, but it was in the transonic area where the tunnels had a problem until Langley engineers solved it.
This was the dawn of the supersonic age. where research would push flight beyond the speed of sound. It was time to take some of the testing out of the tunnels. The U.S. Army Air Force teamed up with Langley and Bell Aircraft to develop an experimental rocket engine-powered aircraft, the X-1.
One solution was to design an airplane to go out and gather the data, and that's what the X-1 was.
On October 14, 1947, test pilot Chuck Yeager took the X-1 on its 50th flight and became the first person to break the sound barrier. Mach 1 was not only reachable, but thanks to Langley and others' research, just the beginning. The future was suddenly coming at us faster than sound, and Langley was up for the challenge of the new high-speed frontier.
At the time the X-1 flew through the sound barrier, it meant a couple of things for Langley. While the wind tunnels were still incredibly important and engineers were still doing that work, now there were these new tools, research airplanes. And so subtly, the mission of the NACA and Langley began to change a little bit.
One of the most brilliant innovations sprang from the mind of engineer Richard Whitcomb. It's called the area rule.
The design concept provides for an indentation in the fuselage near the wing. This indentation reduces the drag at transonic speeds and thus allows the airplane to fly faster and farther without an increase in power.
By the mid-50s, the supersonic age gave way to the hypersonic era and the race to achieve speed above Mach 5. Langley's researchers worked with the other NACA centers, the Navy, Army, Air Force, and North American Aviation, to design, build, and test the experimental hypersonic X-15. The world's first hypersonic research aircraft made its maiden voyage on June 8, 1959.
Mach 5 is hypersonic. And of course, the most famous hypersonic manned vehicle was the X-15. And again, Langley's involved in helping to think about the aerodynamics of that vehicle and in testing it. I mean, it was an NACA, NASA program that really did bridge from the age of the air to the age of space.
The sky was no longer the limit, and whether or not anyone realized it at the time, the space age had begun. As the early X-planes began to scrape the edge of space, Langley aerodynamicists looked even further. The U.S. had much to learn about rockets, and to learn it, Langley turned to one of its up-and-coming engineers.
Well, Robert Gilruth was an engineer, an aerodynamicist, who went to work at the Langley Memorial Aeronautical Laboratory just before World War II. At the end of World War II, he was instrumental in creating the Pilotless Aircraft Research Division. Now, during those early years, they were exploring the flight regime around transonics into supersonic and ultimately hypersonic flight. So it was very much a rocket development organization.
The team's launching of test rockets from Wallops Island, a remote former Navy base on Virginia's eastern shore, was mostly pure research, until the day the mission changed. In October 1957, the Soviets launched the Sputnik spacecraft and stunned the world. The next July, President Eisenhower signed an act to create a space agency. On October 1st, 1958, the 4 NACA research labs, including the newly named Langley Research Center, formed the nucleus of the National Aeronautics and Space Administration. NASA now included a human space program. Langley was its birthplace and became home to America's first astronauts, the Mercury 7.
The Pilotless Aircraft Research Division is assigned responsibility as it is transitioned into something called the Space Task Group for Project Mercury, the first human spaceflight activity. So Langley becomes the centerpiece of the human spaceflight program for the United States. The astronauts are selected, They are unveiled. They are operating at Langley for the first period of the program. They work on the design and research necessary to build the Mercury capsule.
Gil Ruth's group worked through a host of technical issues, like establishing ways to protect astronauts during re-entry and developing simulators to train humans how to work in space. It also created a global communications system to maintain contact with spacecraft. And to streamline operations, NASA's first flight director, Langley's Chris Kraft, applied the concept of something now synonymous with spaceflight: mission control.
That was an idea that goes back to the World Wars, in which flight control is a centerpiece. You have to understand the logistics of movement and how things are going to be operating. All of that can be done from a room, if you will, with communication systems coming in and going out and data coming in and going out. And they modified those ideas from the military and created the modern mission control.
All of these technological advances required mathematical experts. One of the most well-known was Langley's Katherine Johnson. For years, Langley had hired women to operate primitive mechanical calculating machines. Later, those human computers included African Americans, like Johnson, who went on to calculate the trajectory analysis for the first American in space, Alan Shepard. She also verified computer calculations for John Glenn, the first American to orbit the Earth. Her contributions were so great that she was later awarded the Presidential Medal of Freedom. In the 1960s, the space age, born at Langley, took its next giant step, with a little nudge from President John F. Kennedy. Just 20 days after Alan Shepard's historic 1961 flight, the president gives his decision to go to the moon speech.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
It's a technological miracle in many ways. No one's ever even tried this before in terms of reaching the moon. There were three options that anyone could think of. The first option was, let's build a really big rocket, let's fly it to the moon, and then let's land a piece of it on the surface. And that sort of direct ascent option was very quickly put off the table because it was just too expensive and difficult to do.
The second option was called Earth Orbit Rendezvous.
You send up multiple spacecraft into Earth orbit. You convene a armada, if you will, in Earth orbit. They assemble a set of vehicles to go to the moon. They go to the moon, they do their mission, and they come back.
But then a less expensive dark horse candidate arrived on the scene: Lunar Orbit Rendezvous.
In fact, it did not have a very strong following in the senior leadership at NASA in the early 1960s. And a Langley engineer by the name of John Hobolt did the math on this, worked out how it could be undertaken successfully and more easily than Earth Orbit Rendezvous.
Hobolt envisioned a modular spacecraft, launched as one unit. As the main capsule orbits the moon, a lander with 2/3 of the crew would detach and go to the lunar surface. Hobolt's idea won out.
And this is an important decision because this would drive all the technology that would be developed to accomplish the moon program. The Apollo spacecraft, the lunar module landing craft, the big Saturn V rocket were all predicated on that decision.
A couple of years later, Langley trained Gemini and Apollo astronauts how to rendezvous and dock 2 spacecraft while in orbit, setting the stage for the Apollo moon landing. But before anything could land on the moon, we had to know its surface. 5 lunar orbiters took images and beamed them back to Langley.
Well, Lunar Orbiter was an interesting program. How do we get the best imagery that we can possibly get from the lunar surface with a spacecraft that's in lunar orbit, with the intention of First and foremost, finding good landing sites, ones that are safe to land on, but also geologically interesting, so that astronauts can get out of the spacecraft, collect samples, take imagery, and do all of the things that they're supposed to do.
The astronauts also had to be trained to fly the last 150 feet to the lunar surface and then move safely and comfortably in the moon's reduced gravity. 24 Apollo astronauts, including the first person on the moon, Neil Armstrong, trained for their missions at Langley.
Landing on the moon is not an easy task. It's virtually impossible to simulate it here on Earth. They built a huge gantry at Langley Research Center, the Lunar Landing Research Facility, which had cables and hooks and all kinds of things, and you could put a vehicle that was a model of the lunar module suspended from this thing.
Having conquered the moon, Langley turned to the next great challenge: the Viking program to Mars. A mission to investigate the planet's atmosphere and surface and to look for signs of life. NASA Langley managed the Viking project and was responsible for the Viking lander system and mission operations.
The history that it had with Lunar Orbiter, in which it was very successful, sort of gets transferred into the Viking landing program.
A mission to Mars is infinitely more complex than landing on the moon. The Viking 1 and Viking 2 spacecraft, each with its own orbiter and lander, would take months to make the half-billion-mile journey to a rocky, cratered planet that has very little atmosphere. When Viking 1 touched down on the Martian surface on July 20th, 1976, it became the first spacecraft to land safely on the Red Planet and keep operating.
Touchdown, we have touchdown. Exit zone.
Within seconds, it started taking pictures of Mars and itself. What some call the first Martian selfie. Viking was safe on Mars, gathering tantalizing data from another world. The Langley developed technologies that made it possible have continued to shape the robotic exploration of Mars ever since.
It was a very significant coming of age for both NASA and Langley Research Center. Langley was assigned this task and did it beautifully.
By the time Viking 1 blinked out in 1982, the world's first reusable spacecraft, the Space Shuttle Columbia, was starting its 5th mission. It launched on a rocket and returned to Earth like a glider.
Reusable spacecraft goes back to Buck Rogers in the first part of the 20th century. The cartoon strips, the movie serials, the feature films, they all use reusable spacecraft.
Langley's researchers knew about reusable spacecraft from their work in hypersonic gliders and spaceplanes. Beyond testing the preliminary shuttle designs and capturing tens of thousands of hours of wind tunnel data, Langley's engineers also conducted structures and materials tests, evaluated shuttle tire and braking systems, and improved its thermal protection system. From 1981 through 2011, NASA's 5 shuttles flew 135 missions. Its crew transported large cargo to low Earth orbit, launched, repaired, and recovered satellites, and helped build the International Space Station. With astronauts living and working in space since the year 2000, and commercial companies now conducting supply missions to the space station, NASA could focus on deep space travel. With the Red Planet again in our sights, Langley and other NASA centers are working on the Orion crew capsule and heavy lift rocket, the Space Launch System, or SLS.
Mars is sort of the big enchilada of places we'd like to go. And I don't think there's anybody in the space community, and probably a whole lot of people outside the space community, who would like nothing more than to see astronauts set foot on the Red Planet. It's hard to do. There's radiation hazards, there's the microgravity environment that has to be dealt with. All of those are challenges that need to be overcome to undertake a human mission to Mars.
Langley Research is tackling these challenges and many more. Just like the testing of the Saturn V and shuttle designs, SLS models are being tested in Langley's tunnels and with Langley computer know-how. And Langley engineers have led efforts to build a launch abort system designed to carry the crew away in the event of an emergency during liftoff. Versions of the Orion capsule have gone through testing at the same gantry used to train the Apollo astronauts. Splash tests of Orion mock-ups, outfitted with sensors, and some equipped with crash test dummies, will help us better understand what the spacecraft and astronauts may experience when returning home after deep space missions.
One of the things that you have to do is come down in some sort of target area that is within the bounds of the ships that you've got at sea that are going to recover this vehicle. You do not want to leave the astronauts bobbing in the water for too long.
Langley researchers are using all their tools to make sure everything is on track for our journey to Mars. Even as NASA and NASA Langley turn their attention toward other parts of the solar system, scientists never lost sight of planet Earth. Atmospheric science work at NASA Langley began in the early 1970s as an offshoot of its aeronautics research. Langley applied its expertise in tools, methods, and testing toward a science program that would study the impacts of supersonic flight. To understand changes in the atmosphere, scientists first need to measure it. At Langley, some of the earliest measurements started with the 1975 Apollo-Soyuz mission, when astronaut Deke Slayton operated the Stratospheric Aerosol Measurement, or SAM, sensor.
Aerosols are suspended particles or liquid droplets in the atmosphere. Things like soot, dust, black carbon, pollen, those are all examples of aerosols. And though they're really small, they have a big or large uncertainty in the Earth's climate system. NASA Langley has been instrumental in studying aerosols and the processes related to them and understanding their role in the climate system.
The SAM experiment marked the beginning of Langley's space-based studies of aerosols in Earth's atmosphere. Later, more Langley-developed instruments were sent into space. Many were on satellites, like the first Stratospheric Aerosol and Gas Experiment, or SAGE, launched in 1979, part of the family tree of instruments that grew out of the SAM experiment.
The vantage point of space allows us to look at the Earth's atmosphere, its weather, and its climate, to look at various processes ranging from diagnosing our climate, long-range transport, or even improving prediction from our climate models.
Beginning in the 1980s, the space shuttle served as another tool in the Langley Atmospheric Science Toolbox. NASA's first science payload on a shuttle launched on Columbia's second mission. The Langley-developed measurement of air pollution from space instrument helps scientists build a database of atmospheric carbon monoxide levels. These measurements gave scientists a better understanding of pollution and how far it can spread.
The atmosphere is composed of both natural and anthropogenic pollutants. We talk about aerosols and trace gas pollution. These are critical, and we're seeing increases in places like Asia. Meanwhile, we're seeing decreases in other places around the world. So transport and understanding that transport is important to understand the overall climate system and the composition of these pollutants and gases.
The shuttle also carried a Langley satellite-based experiment that measured the planet's overall warming and cooling. In 1984, Sally Ride, the first American woman in space, deployed the Earth Radiation Budget satellite from the Space Shuttle Challenger.
It's important to study the Earth's radiation budget because it has a critical impact on understanding climate change. The sun's energy comes into the atmosphere. It can be absorbed by greenhouse gases. Some of that energy can be reflected. If we end up with an imbalance in our energy budget, we can see warming in our climate system. And that's why the work that's being done at NASA Langley is critical, particularly some of the satellite-based observations.
The Earth Radiation Budget satellite was also carrying an instrument that would take a closer look at the ozone layer. SAGE-2, another in the family of instruments that grew out of the SAM experiment.
The ozone layer, which is a part of the stratosphere, is critical for life on our planet. The ozone layer protects us from harmful UV radiation. Now, in the past, we used ground-based observations and perhaps balloon measurements, but it really gave us point measurements. It's kind of like seeing a tree, but not necessarily seeing the forest. Satellites allowed us to see the true expansiveness of the ozone hole.
Information from Langley satellite instruments provided the most widely used ozone datasets in the 1990s, helping scientists better understand the hole and how to work across borders to repair it. And in February 2017, Langley extended that ozone monitoring legacy with the launch of SAGE 3 to the International Space Station. Another of Langley's tools for looking at the atmosphere is active remote sensing LiDAR technology. Much like radar uses sound waves to take measurements, LiDAR uses lasers. Launched in 2006, the Calypso satellite, a partnership with the French space agency CNES, uses LiDAR to provide new insight into the role clouds and atmospheric aerosols play in regulating Earth's weather, climate, and air quality.
Two of the biggest uncertainties in climate model projections are aerosols and clouds. Clouds can be a net warmer or a net cooler in our climate system, depending on where they're located in the atmosphere. Another key point with clouds is that clouds form on aerosols. Understanding clouds, their formation, and their distribution will take us a long way in closing the uncertainty in those model projections.
Langley scientists have also used LiDAR instruments on board airplanes. It's part of an airborne science legacy Langley pioneered in the 1980s, when scientists first used instrumented planes to better understand the troposphere, the air we breathe.
The troposphere is the lowest layer of our atmosphere. It's the layer that we live in and will never leave unless we are an astronaut or become an astronaut.
Aircraft and the instruments they carry continue to be important to Langley Earth science, whether it's to measure and track air pollution, help assess Arctic sea ice, or study the movement of greenhouse gases. Even as Langley's Earth monitoring instruments fly around the skies, new Langley satellite instruments are in the works, including a new version of Ceres, the clouds and Earth's radiant energy system. Dating back to the late 90s, Ceres and its follow-on instruments are devoted to understanding Earth's radiation budget. Langley is also managing the development of TEMPO, the first space-based instrument to monitor major air pollutants across North America hourly during daytime.
NASA Langley is critical for studying the Earth's atmosphere, given its observations and capabilities related to things like atmospheric chemistry, aerosols, clouds, and the Earth's radiation budget. It also hosts the Atmospheric Sciences Data Center. The data from these satellites, aircraft missions, and otherwise will be critical for closing the uncertainty in our climate model projections.
Learning as much as we can about where we are today will tell us where we're heading tomorrow. Of course, sometimes emergencies arise that no one could have predicted. And in many of those cases, the researchers at NASA Langley have risen to the challenge with timely solutions. Wartime is the ultimate national emergency. And in World War II, Langley earned its wings once again. By methodically examining individual warplanes, engineers learned how to squeeze maximum aeronautic efficiency out of each one. It was called drag cleanup. The magic happened in the full-scale tunnel, starting with the Navy's Brewster Buffalo prototype fighter plane.
This Brewster Buffalo is the classic example. They bring in a plane that's not working the way it's supposed to. It's not performing the way the engineers designed. It wasn't going to meet the basic contract requirements. The real achievement of the drag cleanup study was this invention of a new process for quickly evaluating the performance of a particular aircraft design.
By the war's end, more than 30 varieties of military aircraft flew faster because of drag cleanup.
And you cannot overstate how important that was to the performance of these vehicles throughout the Second World War, and really helped give the Allies an edge in their air power.
Langley's engineering also made a difference in civil aviation.
It benefited the nation and the industry by producing amazing aircraft right after the Second World War, airplanes that could fly faster and farther and higher than anything that had ever been designed in human history.
Those new advancements came at a cost. Vibrations that are inconsequential at lower speeds can be catastrophic as planes flew faster. The vibrations, called flutter, could literally shake a plane to pieces.
And then suddenly in 1959, an Electra fell out of the sky and another one fell out of the sky, and people lost their lives. And this was a profound crisis for the airline industry.
The Federal Aviation Administration ordered tests to find solutions. Industry turned to NASA Langley and its new transonic dynamics tunnel, designed to study the effects of wind gusts and structural vibration on aircraft.
It was a blockbuster test for that tunnel. But what they did in this work was discover the root of the problems. What caused this vibrations? What caused the flutter to occur? And more importantly, how to fix it.
The Langley testing did more than prevent further accidents and save countless lives. It also set the pace for the aircraft industry.
I think one of the really important contributions that Langley made in this particular moment was that it taught industry how to work together productively, how to identify a research problem, how to solve it, and more importantly, it set up a research agenda for decades to come.
Langley's problem-solving expertise was called on again after the 1985 crash of a Delta airliner at Dallas-Fort Worth Airport that killed 136 people. It went down trying to land in a thunderstorm, doomed by a wind shear downdraft, the second such crash in 3 years. The FAA tapped NASA Langley to lead airborne wind shear and microburst detection research.
A microburst is kind of a mini tornado, but in reverse. And wind shear is when those wind currents suddenly shift unexpectedly. Because of these sudden changes, it makes it extremely hazardous for pilots if they're at the point of a flight when they're trying to land the plane. This is when a number of accidents occurred.
Langley developed a system to better understand and analyze these unusual weather conditions.
Langley researchers come up with a numerical scale they call the F factor to help pilots understand the severity of wind shear. That number, this F factor, if you will, is incorporated into FAA regulations today. But it's a great example how one piece of research can have national impact.
Because of NASA Langley research into sensors that warn pilots a microburst is ahead, wind shear accidents in the US have been virtually eliminated. But it's not just outside agencies that rely on NASA Langley's expertise. After Challenger exploded in 1986, Langley engineers tested the solid rocket booster's failed O-rings. Other Langley researchers focused on the booster joints and came up with a whole new design. After Columbia was lost during re-entry in 2003, Langley wind tunnel and computer-based studies of shuttle aeroheating helped paint a picture of what happened. Langley then focused its technical strengths on shuttle's thermal protection system, what made it fail, how to inspect it, how to repair it in orbit, and determine when it was safe to fly, even with minor damage.
So after the shuttle accidents, one in the mid-1980s, the other in the early 2000s, NASA Langley engineers worked together to find solutions to incredibly complicated technological problems. They even developed a camera that could inspect the shuttle while it's in orbit. But the most important contribution they made was helping the United States return to space.
And during the shuttle's final missions, Langley researchers took images unlike those ever seen of the shuttle. Thermal snapshots at Mach 20 that may someday be used to create new spacecraft.
Over the past century, NASA Langley has gained an outstanding reputation for its responsiveness to national emergencies. I think the reason it's been so effective is its people. They're resourceful, they're imaginative, they're creative, and above all else, they have the remarkable capacity to reinvent themselves. It's those qualities that make Langley such a national treasure, and it's what augurs well for the future.
From the beginning, NASA Langley has been in the business of shaping the future. First, we conquered the air, then the sound barrier. After that, the moon. Next step, Mars and beyond. While we've celebrated successful Martian landings, starting with NASA Langley's Vikings in the 70s, and more recently, rovers like Spirit, Opportunity, and Curiosity, future missions will require larger craft, bigger payloads, and eventually human explorers. That will demand improved entry, descent, and landing, EDL technologies that must slow a Martian lander from 16,000 miles per hour for a safe and precise landing. Langley's EDL experts developed and built a heat shield sensor that flew to Mars and will help researchers design future spacecraft. Other game-changing Langley inventions for planetary exploration include lightweight inflatable spacecraft heat shields, inflatable habitats, and next-generation rovers that will allow humans to live and work on other worlds. Langley Research Center has already started building the future, using robots to help create new structures. Langley chemists are also developing the next generation of materials, incredibly strong and lightweight, that could have wide-ranging uses in spaceships and everyday life. But Langley has not forgotten its aeronautic roots or its commitment to X-planes. Almost 70 years after Chuck Yeager broke the sound barrier, Langley is working with industry on a supersonic passenger jet that would transform the sonic boom into a neighborhood-friendly sonic thump. Today's and tomorrow's X-planes have progressed to numbers like 43, the fastest air-breathing aircraft. The X-48, a new aircraft concept designed to be greener and more fuel efficient. And the X-57, the first all-electric aircraft. All are being tested or developed at NASA Langley. On a smaller but perhaps even more ambitious scale, Langley engineers are looking at concepts like personal air vehicles and drones that require the development of intelligent autonomous systems that can allow machines to learn and act independently. Other Langley visionary research will explore new ways to better understand our home planet. Langley scientists are developing low-cost, small satellite technologies to observe the climate and air that we breathe. Sensors and instruments on spacecraft, aircraft, and on the ground, combined with computer modeling, will help us better predict and understand conditions here on Earth, and will continue to add to our long-term climate data records, so critical to understanding our planet.
100 years ago, NASA Langley rose from the farmlands of Hampton, Virginia, to become an aerospace research powerhouse. The trajectory of Langley's mission has carried it beyond the sound barrier, beyond our atmosphere, and even beyond the moon. All the while, NASA Langley's advances in materials and atmospheric science are improving life right here on Earth, expanding our knowledge and protecting the planet. Whether pushing the envelope of science and engineering or responding to national emergencies, the people at Langley are already hard at work shaping its next 100 years, transforming science fiction into reality.